Organic polymers are major features in our lives. They surround us every day, forming many familiar objects. You've only got to look around this car to see that large amounts of it are made from synthetic organic polymers, or plastics as they're more commonly known. In fact, around 3.5 million tonnes of polymers are used every year in the UK alone.
Polymers are large, complicated systems whose properties are determined by molecular construction and interaction. They may be hard and tough, or soft and flexible. Modern technology has allowed the chemists to manipulate these properties and to create individual polymers with very specific uses.
What we'll do in this video is see how the molecular structure relates to the physical properties of polymers. And where better to find a vast amount of organic polymers than in the supermarket?
Polymers are large molecules built up from small repeating units which come from monomers. All living things use polymers as their building blocks. Proteins, polyketides, polyisoprenes and polysaccharides are all important structural materials in both animals and plants. But what we're most interested in is the packaging, the commonest application for synthetic organic polymers. The basis for most organic polymers is a hydrocarbon chain, and in the case of polyethylene, or polythene as it's more commonly known, the simplest man-made polymer, the substituent atoms are hydrogen. Carbon bonds strongly to itself, making the chain strong, but because the carbon backbone is zigzagged and the bonds can rotate, it's also very flexible, producing long coiled polymer chains. Changing the substituents of this carbon backbone is an obvious way we can alter the properties of a polymer. But as you'd expect, it's actually a lot more complicated than that.
As we have already said, polymers are large molecules built up from small repeating molecules called monomers. And there are two main processes for joining the monomers together. The first of these is called free radical addition. Free radicals are capable of reacting to open the double carbon bond of a monomer and adding to it, leaving an electron unpaired at the other end, which in turn opens the double bond of an adjacent monomer. In this way, many more monomers can add successively to the growing chain until by chance two active ends combine, creating one molecule from two growing chains and terminating the reaction. The second method of polymerization is called condensation or step reaction polymerization. This takes place between bifunctional monomers, monomers with a functional group at either end. These can be combined, eliminating a small molecule, such as water or hydrogen chloride, to produce short-chain intermediates. Short chains then link to form larger polymeric difunctional molecules, and the reaction continues until an equilibrium is established. This process is slower than free radical addition and commonly used to produce polymers such as nylon.
One of the most widely used polymers is polythene, as it's cheap and easy to process. It also has the simplest structure of any polymer, so let's see how we can use it to affect the properties of polymers. These both made of polythene, but they behave very differently.
The long molecular chains of most polymers, including polythene, are not actually bonded together but held by van der Waals forces. These forces occur wherever molecules are close together and have an electrostatic, weakly attractive nature. Polymers are predominantly amorphous. In other words, the molecular chains form a random, irregular structure. However, particularly in polythene, with its relatively simple structure, sections of the molecule chains can pack close together, forming ordered crystalline regions surrounded by disordered amorphous areas. These crystalline regions are stiffer and stronger as they maximise the van der Waals forces, so high crystallinity makes the plastic stiffer.
Crystalline regions also disperse light, preventing it from passing through the polymer. So when there are both crystalline and amorphous regions, the size of the crystallites determines the degree of transparency. Large crystallites make the polymer translucent, and the smaller the crystallites get, the more transparent it becomes. Of course, it could be completely amorphous with no crystallites, and this would lead to a totally transparent polymer, although you could make it opaque by adding dyes. So flexible long-chain molecules, the lack of covalent bonds between them and the degree of crystallinity help to determine the flexibility and strength of the polymer, as well as its transparency.
But why should one polymer be more or less crystalline than another? Crystallites tend to be formed when polymer chains are symmetrical and can easily pack together. The basic polythene molecule we saw earlier is perfect for this, and is in fact highly crystalline. But the active end of a growing chain can also break into another chain by displacing one of the hydrogen atoms instead of splitting a carbon double bond. This leads to branched molecules as opposed to perfectly linear chains. And the size, position and frequency of these branches has a serious effect on any crystallites, and therefore affects the properties of the polythene. Low density polythene, LDPE, has random branching of both short and long chains. This irregular structure prevents too many crystallites, and so the polythene is very flexible but tears easily. In contrast, linear low density polythene, LLDPE, has regular short chain branches. Being symmetrical, they can pack together more easily and give rise to small crystallites, making the plastic stronger and more tear resistant than low density polythene. High density polythene, HDPE, has minimal branching and therefore it's highly crystalline. It's less flexible but more durable and widely used in commercial products.
So, even with an apparently simple molecule like polythene, the properties can vary dramatically by controlling the degree of crystallinity. But obviously things can get a lot more complicated than that. Polythene has only one stereochemical arrangement due to its highly symmetrical nature. But what happens if we exchange one or more of the hydrogens on the monomer for a different substituent? For example, if one of the hydrogens is replaced by a methyl group, the resulting polymer would be polypropylene, and three different stereochemical arrangements can be formed. Atactic polymers have a completely random configuration. Syndiotactic polymers have a regular but alternating form, and isotactic polymers have all the substituents to one side. Each form has very different properties. In the case of polypropylene, the atactic form, with its lack of stereoregularity, is completely amorphous. It's a soft, transparent, viscous liquid with little use commercially. In contrast, isotactic polypropylene is fairly useful commercially. It is highly crystalline due to its regular nature. This makes it durable and fairly rigid. It is also heat stable and chemically inert, which makes it useful for food packaging.
So far, it seems that the more crystalline polymers are of more use. But what if we want to take advantage of a polymer that's normally too stiff for the purpose we want to use it for? Take PVC or polyvinyl chloride, for instance. Normally, atactic PVC is a stiff and glassy polymer, rather like this polystyrene box. So how can we make it more flexible and stop it from becoming glassy? By including additives called plasticizers, we can make polymer chains much more flexible. Plasticizers are high molecular weight organic solvents, and they act as spacers and lubricants at the molecular level. They prevent chains from packing close together, and thus the formation of crystals. So by adding plasticizers to PVC, we can make it suitable for food wraps, like this, or for the flexible coverings on electrical cables.
All the polymers that we've looked at so far come under the general heading of thermoplastics. This means that because the molecular chains are only held together by van der Waals forces, they will melt on heating, a very useful property in itself. They can easily be moulded into shape, making them ideal for an enormous range of applications, from simple packaging to quite complicated products. More importantly, thermoplastics can be recycled. When we're finished with one product, we can simply melt it down and reshape it into another product, although eventually the desired properties will be reduced by recycling. This bottle is made from high density polythene. We can tell by this triangular symbol on the bottom. The most common plastics have their own identification symbol to make recycling easier. Sometimes the symbol appears with just the code number or the code letters for the plastic, or it could show both.
The one thing all thermoplastics have in common, no matter how amorphous or crystalline, is the lack of any covalent interactions between the polymer chains. However, some polymers benefit greatly by introducing chemical crosslinks, and rubber is the perfect example. When you stretch rubber, the long carbon chains uncoil until the crosslinks prevent the chains from slipping past each other any further. The chains are now in a more ordered linear structure with lower entropy. As you release the force, the rubber is restored to its original length because the law of entropy favours the more disordered coiled form. Not surprisingly, these types of polymers are called elastomers, but how do we add the covalent crosslinks? Rubber is formed by a naturally occurring addition reaction between isoprene monomers. In fact, it's the cis form of polyisoprene. The chains cannot pack close together, slipping past each other with relative ease, so it's completely amorphous. Sulfur is added, normally about 10% weight, creating covalent crosslinks between the polyisoprene chains. This process is called vulcanization, and it makes the rubber much more durable and elastic. Polyisoprene also exhibits a transform called gutta-percha. The trans polymer chains can fit together to form crystallites, making it much more rigid than rubber, and it's often used as a covering for golf balls.
So now we've seen two different classes of polymers: thermoplastics, which can be melted and moulded, and elastomers, which are amorphous but with some covalent crosslinks between the chains. But there's one very important characteristic that's common to all polymers and vital when determining polymeric properties for any specific application.
All amorphous polymers, even the amorphous regions of those polymers which contain crystallites, can assume the characteristics of glasses at sufficiently low temperatures. The temperature at which this occurs is called the TG, or glass transition temperature, and as you can expect, it varies from polymer to polymer. Below its TG, a polymer is hard, stiff, and, most importantly, brittle.
At room temperature, our rubber band behaves normally because it's above its TG. But if we cool it in liquid nitrogen to below -70 degrees Celsius, the TG for rubber, it undergoes the glass transition and becomes brittle. The Challenger space shuttle disaster in January 1986 was caused by a polymeric sealing ring undergoing a glass transition due to an unexpected frost the night before. The seal became brittle during the flight, cracked, and leaked fuel with disastrous results.
The TG of a polymer can be affected by plasticizers, remember making PVC more flexible. It can also be affected by covalent crosslinks between chains. Crosslinks restrict chain mobility. This increases TG. The more crosslinks are present, the higher TG becomes. In fact, some polymers have so many crosslinks that TG cannot be reached.
Which brings us on to the next class of polymers we're going to look at. Thermosets are completely amorphous but very highly cross-linked polymers. Unlike the polymers we've seen so far, thermosets are produced using condensation or step reaction processes, and due to their cross-linking they have a very high TG with very little flexibility regardless of temperature. One of the earliest synthesized polymers, Bakelite, was a thermoset. Common examples of more modern thermosets are epoxy resins, like araldite. Araldite consists of a compound containing epoxide rings and a curing agent. When the two are mixed, reactions occur that open the epoxide rings, and each molecule forms several crosslinks to other molecules, essentially forming one giant macromolecule. After a short time, a hard thermoset is formed. Thermosets are very stable and have good resistance to heat. In fact, heating sometimes causes even more crosslinks to be formed, so unlike thermoplastics, they can't be reused. Their stability and heat resistance, however, makes them ideally suited for the manufacture of electrical fittings. But the products need to be moulded during the reaction stage, whilst the polymer is still viscous.
So far, all our thermoplastics have been made from repeating a single monomer, but by regularly alternating two different monomers in a single chain, a very important group of polymers are created. The word nylon is a generic term used to describe synthetic polyamides, formed from an amine and an acid using a condensation reaction. They are called polyamides because the monomers are joined by an amide link. Essentially, polyamides are thermoplastics composed of highly symmetrical linear chains which crystallise easily, making them ideal for extrusion into fibres by orientating the chains and crystals along an axis. However, unlike the other thermoplastics we've looked at, polyamides also have intersegmental hydrogen bonds at regular intervals, giving the fibres very high tensile strength. Nylon 6,6 is prepared from an amine with 6 carbon atoms and an acid with 6 carbon atoms, hence the name. It's one of the most widely used nylons for clothing. Other nylons, such as nylon 610 and nylon 611, are made from starting materials with different numbers of carbon atoms. Changing the length of the monomers, which means changing the distance between the hydrogen bonds, alters the polymer's properties, such as making it harder or softer, more or less resistant to solvents, and even changing the melting temperature. In fact, nylons or polyamides are very versatile materials. Although they are ideal for extruding into fibres, their uses aren't solely restricted to fibre applications. Kevlar is a particularly strong fibre and is used in police body armour. It can also be used with epoxy resins to make an extremely strong fibre reinforced plastic.
All the polymers we've seen so far have had one kind of repeating unit. These polymers are called homopolymers. But there's one final class of polymers that we still need to look at. Copolymer is the name given to a polymer produced from 2 or more different kinds of repeating units. This process enables us to produce new polymers, which combine the properties of more than one polymer.
We can create copolymers in 4 ways. Random copolymers, where the repeating units are randomly arranged along the same linear chain. Alternating, where the units regularly alternate along the linear chain. Block copolymers, containing long sequences of the different homopolymers in a linear copolymer form. And finally, graft copolymers, which have a backbone of one homopolymer with branches of other homopolymers grafted onto it, much like the branches of polythene we saw at the beginning. Let's look at just a couple of copolymer examples.
If we graft polystyrene and acrylonitrile onto a backbone of butadiene, a monomer used to make natural rubber, then we can create an ABS resin. ABS is a so-called rubber toughened plastic. It's often used for things like telephones, as it's much tougher than ordinary thermoplastics. But there's another important copolymer, which also involves butadiene. A random copolymer can be formed with butadiene and styrene along the same continuous polymer chain. It's called SBR and is used in tyres. SBR has non-crystalline properties between those of a thermoplastic, the styrene, and those of an elastomer, the butadiene. Altering the ratio of styrene to butadiene produces polymers more suited to different parts of the tyre, whether they need to be more hard-wearing or more flexible. Obviously, copolymers can open up exciting new possibilities to produce very sophisticated polymers. A lot of research is pursuing this area.
Hopefully, you can now start to see the potential of organic polymers with their wide variety of properties. We've looked at how polymers are processed and the difference between thermoplastics, elastomers, thermosets and copolymers.
Thermoplastics have no crosslinks, so they can be melted and remoulded.
Elastomers have light cross-linking and return to their coiled form after stretching.
Thermoplastics are very highly cross-linked, creating one large macromolecule. They can't be melted and must be moulded while still viscous.
And copolymers allow us to produce polymers with combined properties.
We've seen how the properties of polymers can be drastically altered by using cross-linking, plasticizers, or different stereochemical forms of the same polymer, and many other techniques.
In fact, we hope we've given you an idea of the enormous range of possibilities presented by organic polymer chemistry and some of the science behind the everyday objects that you see.
Try to look at things and work out why a certain polymer has been used and what makes it have the right properties. Polymer research is a rapidly expanding area. We've obviously only just scratched the surface with this video. There's still so much more to be discovered.